They include populations of agents in the form of main, and there'll be some other elements that are active objects as well. So when we have a model, the main class and the agent classes will be active objects. Each of them will be subclass in the active object class. Active objects support the common functionality, being depictable, being nestable, so you can put one inside the other in a nested hierarchy, for example, being connectable. This X means an experiment. This is one type of experiment. We'll come to some other types of experiment later in the class. Parameter variation experiment, Monte Carlo, ensemble experiments. But this is one experiment. It's a single scenario run. AnyLogic in contrast events and makes that explicit, that you have these objects that represent scenarios. And you can go back and rerun them very readily. Okay. So we should see something along these lines when you call up AnyLogic. Now I'm going to go over here and okay. So my AnyLogic is exhibiting. Maybe it's not yet up. I'm not sure what's going on there. Okay, so I'd like you to add in an active object class to this. So what you'll do is you can do file, or excuse me, just go to model and add in active object class. And you'll notice it's the first of these elements, and we'll be adding this actually for the agents, okay, for the person agent. And you'll pardon me as I just go and try to figure out where my AnyLogic's at here. Okay. Okay. Here we go. Okay. So I'm gonna go duplicate just what I did there. So I just minimized that splash screen, and I am doing new model, and we'll do first CMPT 394 model. I know it's something different, and I'm just going to start this. And so here it's creating this. And importantly, these are classes. So we're dealing here firmly in the province of object-oriented programming techniques that will come up again and again and again. And here we have a main class and a simulation class. If I right-click on this guy, I can do new active object class. Alternatively, I believe I can do it through this as well. Yes, file new. So typically there's several ways to do it, but I'm just going to add in an active object class. I'm going to call it person. Okay, and you'll notice that that's created with the same little icon. The difference is going to be under the general tab. I'm going to declare it as an agent, and when I declare it as an agent, can you see what changes over on the left-hand side? I'm clicking this back and forth. Can you see anything changing? Over here, this is actually changing back and forth from just being an A to something that looks like Da Vinci's measure of man. And that's an indication that this is an agent. Okay, this is going to be our agent class. It's going to find agenthood. It's going to find agentness. In all the typical way, we look to a class to define the characteristics of the particular instances of that class. Generally, our class might have a lot of heterogeneity associated with it, but we'll create a single class for things that exhibit similar types of behavior that differ only in degree. Like they differ only in based on the current status of a person, their age, or whatever. It differs in that characteristic. If we have different types of agents that differ qualitatively with respect to the types of behavior available, etc., we'll reflect them in a separate class. Okay, but here we have a common class, and so we're checking the agent here. Now, some of you may recognize this interface. Does anyone recognize where this interface comes from? Where have you seen an interface like this? What does it remind you a little bit of? In terms of the design of these guys here. Yeah, it's Eclipse. This is Eclipse RCP, Rich Coin Platform application. It runs atop Eclipse, basically. And it's leveraging Eclipse under the surface for things like autocomplete, etc. You'll notice, per other standard conventions, a star means it's not saved yet, etc. And we're going to have over here this broad palette of elements. And I argued before that the agent-based modeling vocabulary is much larger than the system dynamics vocabulary. And some of the things you'll see here will testify to that. You'll actually see some system dynamics elements here, stocks, flows, etc. But you'll also see things like parameters and events and variables and collections and functions and connectors, ports, state charts, etc. These will be elements that we'll be seeing more and more of over the course of coming lectures. Okay, so continuing right along here, there are several windows, and these should be familiar to you. So you have a project window that shows in a hierarchical fashion the projects. There's a problem window that indicates build problems. So when your model won't compile, ends up here. There'll be a console window down here. In a properties window that shows the properties of the current selected thing. The console will give output from your running model. Problems will be used for build-related problems, so syntax errors, issues with the semantics of the program, so type checking issues, etc. There'll be this canvas up here in the middle, which is going to hold descriptions of agents. Descriptions of the global environment, descriptions of intermediate things like schools or cities or what have you, and however high you want to make that hierarchy. And you're going to drag things from this palette over here on the right and drag them onto the canvas. And one of the things we'll see is that within AnyLogic, agents have a visual depiction as well as a logical set of characteristics. And that visual depiction will have representation both at build time, that is when we design the model on the one hand, but it will also have, it will also carry over to runtime. So agents will have an appearance at runtime that's useful for visualization. And it's not merely eye candy. I know as an engineer, early on, I kind of saw a lot of it as glitz. Why do I really need to see these agents? It turns out the longer you spend with this, sometimes it just comes out and hits you when you get to see the visualization of it, what's really going on. Some of the effects like spreading across networks, percolation, or the visual effects, they might have been going on, in arrays of stocks and flows before in a system dynamics model. They might have been going on in MATLAB if I had represented it as vectors, but I wouldn't have seen it and I wouldn't have grasped what was going on. I have some real big cases where this has occurred, and it wasn't until I really saw a depiction, and then I immediately said, okay, that's what's going on. It's very obvious. No more questions as to what's happening here for explaining these dynamics. It just makes it very obvious. Fortunately, AnyLogic also provides you a way of turning that off when you don't want to see it. So if you want to do a run where you don't want to see the visualizations, it's very easy to do it, and that will improve performance greatly. Because keeping around those visualizations, the representations of people connected into networks, it's expensive. So one thing you may want to do is, if you have any problems seeing these, if you go to the View menu, you can enable which of these windows is enabled and disabled, and you can hover over the minimized ones to see to re-enlarge things. Okay, so in the project window, we have several types of entities shown. One is the main class. This is the stage in which the agents circulate. This is the global environment associated with the agent. And there may be one or more agent populations in there, and we'll see in a second how we add those populations. There's agent classes that define the actors, and then there's experiment classes of various sorts. We're going to concentrate right now on experiments which are single run experiments. So they're single scenarios. They run the model with a certain set of parameters. End of story. Okay? Certain set of assumptions. And typically they're defined by parameters. Parameters will be the way of simultaneously communicating assumptions and describing constants that don't really constants within the model, or things that change very rapidly. So we're going to be dealing here with the main class, agent classes, and experiment classes. And as you'd expect, if you have a model with multiple types of agents, maybe it's people and deer to represent hunters and their quarry, they'll each be agents in a subclassing sense, in a subtyping sense. They can be passed around as agents to methods. There's a whole agent library that applies to both those sorts of agents, etc. They can both be connected in networks, etc. But they're going to be different subclasses implementing the agent interface or subclassing the agent class. It's actually agent, a 2D agent class in that case, if it's in 2D. And they're going to be associated with visual representations, okay? So I'd like you to double-click the canvas, or double-click this for person. It will open up this canvas, okay? And we're going to see this, this class. We don't need to talk about that. Okay, critical distinction. Just as with any sort of program, you're going to distinguish here between design time of the program and up to compile time and then execution time. So you're going to be specifying the model and you're going to be running it. No surprises here. And it's important to be clear in sort of what applies at what times. Okay. There's going to be classes that are going to have design time and runtime elements. So, for example, we're going to have events in our model. And those events will have a representation at design time. We'll see that we've added an event to our agents, or we'll have a state chart. And that event will be represented at design time in our agent class. But then when we run the model, we'll see that same state chart represented visually as well. Okay, so let's just see an example of this. So if we go to our model here, let's go add a state chart in. Okay, so let's drag in. So I double clicked on person. Here's person, and then I'm just going to drag in a state chart entry point, which is located partway down here. And I'm going to drag in a state here, and maybe this is going to be, susceptible, and then this will be, afflicted or something like that. We don't necessarily want to assume that it's by infection. Okay, so all I've done is I've dragged these two in, and I made sure that this guy is connected there. And now what I'm going to do is I'm going to add a transition between these two. Okay, and there'll be semantics associated with this transition that we'll get to pretty soon. But basically, I can define what sort of transition is it, and some of these will be your old friends, particularly rate. A rate transition will be your old familiar first order delay. It'll be your old familiar chance per unit time of going. There'll be a timeout, which is you leave after a certain amount of time. There'll be conditions and based on message arrivals and based on agent arrival based on mobility, which will be a fun set of things to look at. Okay, so now we have these agents, and you want to be sure that these things are connected properly. It may look very close together, but unless it's green when you move it there, it's not properly connected. Okay, so we have this specification of a state chart within an agent, and perhaps we give it a rate of 0.1. So if I told you that the concept of rate is there's this chance per unit time of going from one to the other. So here you have a chance of a likelihood of 0.1 per unit time of going from susceptible to afflicted. For how long are you on average in susceptible? Yeah, 10. 1 over that thing. It's the same old story we saw before. What's different is, this is a little bit like a first order delay. What's different is this is applying at an individual level. The individual is either in this state or that state. Their likelihood of being in this state declines as a first order delay. But, okay, so now let's run this thing. Okay, I have the state chart. Let's run this. So right click on the simulation experiment, and we're going to run this, okay? And when you run it, you should come up with a screen like this. So let me do that again if I was too quick there. So after composing this, as long as there's no problems there, and it'll be unhappy if you have anything disconnected. It will say not reachable, da da da. So you got to make sure there's no problems. Okay, and then right-click on this guy and run it. There's also other ways to do it. For example, model run. You could do that, and you could select which one you want to run. Okay, so let's run this guy here. So here we go, and we have an interface here which allows us to actually specify further things like whether we want to keep track of the model time and so on. And we could also specify here using sliders and so on model assumptions. And now we're going to see the model running, but we don't have any people in it yet. It's all blank. So we're going to go change that. Just because we added a model class doesn't mean we have a population. That's the lesson there. We have personhood, but we don't have actual persons defined. So how are we going to add a model class, a model population? Well, open up main, because main is where, by default, the populations are going to live. Again, populations could live within a city class, and the city class could have neighborhoods in it, and the neighborhoods could have people in it. We're going to get to that. But right now, the most natural place is to put them in the global environment. So we're going to add a population of persons. Okay? How are we going to do this? We're going to drag the person class into the canvas for the main class. Okay? That is the key thing. So in main, we drag that in, and let's call it population. Okay? And you'll notice here that when you do that, so I double-clicked main to open up the main canvas, and I dragged it in from person. The key thing to note here is that we have a thing that looks that same icon of an agent, but we're going to make it a replicated population. So we have to go in the general properties for it and click replicated. And let's make it a population of 100 agents by default. Okay, 100 agents within this. Okay, so there's going to be 100 agents within this population. Now we can run this model, and there will actually be people. Okay, so if we run the people, we actually see there's a population here. If we click on it, we see, oh, okay, there's 100 active objects in there. That's that whole notion of active object that gave us the A. In fact, if we go to this navigation menu up here, we can drill down and see individual population members. And by the time that I've come to it, well, not all of them. Here's one: susceptible, afflicted, and we can click up over time. Most of them are now afflicted. Okay, so here we have a situation where we have a population, but the agents don't have a representation visually yet within the screen. We're going to add that in just a few minutes here. But we have a model that runs with a population. That's a good start. Okay. So I think what I'm going to do is, oh sure, okay. So double-click person, and what I'd like you to do here is I'd like you to drag from the palette window, but you're going to have to scroll down to the presentation area, and I'm going to pick an oval, and I'm going to drag it over there and place it on the origin. Okay. What I've just done is lend this person a visual representation. Okay. I've given him a visual representation. He had a logical representation before in some of the behavior, but I've just given him a visual depiction. Okay, and that's this oval. And it turns out AnyLogic has got some really powerful features that allow you to associate dynamic properties, so this oval can change things over time. But let's go play with this some. First thing to notice is, and this is a point of warning, if you go and run this model now, and you run it, you won't see anything different. It looks the same. And by the way, I can right-click over this and drag around, so I can kind of scroll around within this, see if things are around elsewhere. So you won't see anything initially. And the problem is, folks, that we have actually added that representation of the person after the person was added to this population. So to deal with that, you could either add their visual representation before adding them. You can refine it later. Or you can click on the population and do create presentation here. Okay? So you have to go to main, go to the population here, and you can do create presentation. And that will actually create the presentation that you added after it was added in. So that's just to kind of resync it. Now, if we were to do that, and we were to run the model, what we would see is something which is where we have a population. In fact, all the people are sort of superimposed within this single circle. Population member 1 is there, population member 2. They're all in different states as per chance, but they've all got this representation located at that choice. We'll get to the issue of environments and explicitly declaring an environment that handles their physical layout and that sort of stuff in a little bit. But right now, they're all located at the same position. It's very easy to insert some code that will change that or to do it declaratively. Okay, so let's talk further about this. So main class are the stage for agents, and we set the replication property. Okay, so we added these folks in. So we simulated this model. Okay, so I think what we're going to do now is we're going to drag in an environment. Okay, so we'll go up to the top here, scroll up, and we'll notice that there's an environment down in the top thing. This goes into main as well. It's very important to be clear of what things you're adding these to. We're adding this to main. Environment affects this population, and therefore it exists at the population level, and therefore it's in main, not in the individual agent. So we have an environment, okay? I dragged it from here. This environment allows us to specify various things about the spatial layout, the networks that we want to use, etc. For now, that will be all we need. Just the default sort of fact that it, by default, puts people at random locations in continuous 2D with a certain size. But we'll come back to this when we look at different types of networks and their dynamics, etc. So we added this environment. For the population, we want to specify the associated environment. So we want to say that the environment is this environment. Now I want to note something here. When we actually going to specify that, so I went and I clicked on the population icon here within the main class, and it called up this general property, and I typed in environment here. You'll notice there's this little component here, which is a light bulb. And it says use index a replicated person. What that's actually giving me a hint is for some Java code. And what I want to bring out here is a big contrast to what we've seen in Benson. A tremendous number of the fields here in AnyLogic that appear to be fields where you have to type names, you have to type numbers, are actually general Java code. You put in expressions. They're Java expressions. This is a Java expression. It just happens to be one that's constant across all environments. But if I wanted different environments to apply to different agents, I can make the environment be a function of the agent. In other words, have an expression that says, well, if index is less than 50, use this environment, otherwise use that environment. I could call a method that assigns the environment for the agent. Okay, so I've just specified the environment there. Okay, anyone want me to pause to resolve an issue? People comfortable? People good? Okay, so if we do this and we run the simulation now, what we should actually see is rather different. Now we have these agents spread out randomly in space, and a given agent will be at different positions from one another. We'll have the different agents located, spread out around space. Now it turns out that by frobbing the features of that environment, we could lay them out in different ways. For example, we might want to, instead of doing a random one, which is actually the default one, we could do an arranged layout. Now in this case, it's going to arrange them into, it's going to array them by rows and columns, array them in that sort of layout. And in other cases, we may want the layout to depend on their connectivity to each other. So we locate people who are close together in some network, or we may want to arrange them in a ring for so-called ring lattice type models, where they're all arranged in a ring, where it's very localized connections. Each person perhaps is connected with those on either side of it, but no further. But for now, we'll leave this as a user-defined layout type. Okay. So the environment is a very powerful thing that allows us to lay things out differently. So we've told the population to let the layout base it in there. Okay. So I think I will probably go light on. Well, sure. Let's do that because it's a good illustration of these properties. Okay, so folks, what I'd like you to do next is for network type, I'd like you to select distance-based. Okay, so I'm going to environment and under network type, not layout type, but network type, I'm selecting distance-based network. And what that's going to mean is people should be connected together if they're within a certain distance of each other for a network. So it's going to build a network for us automatically based on their layout, based on their locations. Specifically, two people, person A and person B, and person B will be connected if they're located within a certain distance of each other, and that distance is 50 units of distance. Each one of these little squares here is 5 units on the screen. So here we're going to ask them to be connected if they're within 5 units. However, before we can, well, it turns out that if we run it in this way, we say, okay, I'd like them to be connected if they're within that distance of each other. Turns out they're connected. We just don't see it. We don't see it visually, okay? If we want to see it visually, we're going to need to have them be associated with some ways of showing who they're connected to, okay? And we're going to see how to do that. First, I want to frob this visual representation so we can make it more less intrusive. Right now, they're a big kind of blobby thing. I'm going to go down to person because it's a person characteristic, opening person, and I'm going to shrink down this oval to be a fraction of its previous size, and I'm going to center it at the origin. Okay. Why at this origin? Because this is the point of reference. This is the origin for that person. If they're located logically at point 1010, and we locate something visually here, when they are depicted in the global environment, that thing will be centered at 1010. Okay, so this is the origin of their local coordinate system, this sort of area right up here. Okay. If we located something over here, they'll be displaced by that amount from their logical position. For now, we just want them on their position there. Okay, if we run this now, having shrunk them down, we'll see a more tractable picture, but we still want to have depictions of networks. I want to see those networks. So, ladies and gentlemen, let us compute. And compute we shall. Okay, so in order to depict a network visually, we're going to need another visual element, okay? So I want to open up person, and I want to go down to presentation in the palette, and I want to drag in a line. That's how we're going to depict people as being connected with lines. Okay? Lines are going to be how we have this connection, this edge between two vertices. The vertices are the ovals, the edges be depicted by the lines. Okay, the connections. So we're going to go down to the presentation here, and here we go. We're going to drag in a line to person. Okay, now this is a little bit tricky because what you want is the plus side of the line to be in the center of that oval. That's actually the sort of the origin of, or the source of the line. The other is the destination of the line. So you want it to come from here to there. It's actually a direct line. Okay, and so the plus side, you'll notice one side is a dot, one side is a plus. So you want the plus side to be there. Okay. to be in the middle of the circle. Okay, and so it should look something like this with this plus there. Okay. Okay, so if you originally drag it, then drag it there. Okay, now if we run this model, we'll see an uninspiring sight. Uninspiring, it'll look like a bunch of lollipops, which is a start, ladies and gentlemen, but it ain't where we want to go. So we're going to continue on. So we're going to need to multiply and adjust the lines. So the issue here is two things, logically. So what's wrong with this picture? Who could tell me? What's wrong with this picture? What's inadequate? Okay, and there's two problems with it. What are the two distinct problems? Well, let me just end your misery. The two distinct problems are, number one, they don't have a line for each connection. They have just one line. They may have 0 connections, they're shown with one line. They may have 10 connections, they're shown with one line. That's all. The second issue is, for each connection, it needs to connect to the appropriate agent, right? So we need a separate line connected to the appropriate destination agent for each of their connections. Does that make sense? Okay, ladies and gentlemen, let us do that. And fortunately, and this will alert you to some of the flexibility of this approach, this can be done significantly in a declarative way. So, ladies and gentlemen, let us go click on the line that you added, the line segment, which, by the way, can be arbitrarily oriented. I'll pull it this way just so we can see it more readily. So click on that line and then go to the dynamic properties of that line. Okay. These dynamic properties will be things that you can specify job expressions for, and it will automatically recompute it over time. Okay. So one thing is going to be the replication of the line. How many lines do we really want at runtime? At build time, at specification time, all we're going to have is one line. But this is going to turn into several lines. How many lines do we want? Tell me. Number of connections. Okay. So we want this dot get connections number. Okay. Get connections number. And you can see it does the autocomplete. Control space or command space, I think, on Macs. Command. What is it in Eclipse on Macs? Remind me.
Looks like it's
Option space. Okay, thank you. So under replication, you can use option space for this document. So I am an agent. This person is an agent class, and therefore it has a method called getConnectionsNumber. If you want to see the information about it, it applies to agents, and here's the Java docs on it. Returns the number, and you'll notice it applies to an agent. Okay. So now we're going to have replicated agents for each one, and then for each of those replicated agents, we want that line to point to the appropriate destination agent. So if we scroll down, we could see we have many properties. We could change the color of the time. Over time, we could have it respond to on-click events. We could have the width of it change, etc. But we're going to go down to this dx and dy one. Okay. Now you'll notice that this tells us again with the thing, we can use index to be the index of the replicated line. So now it's telling us essentially, hey, you can refer to, for line 1, line 2, line 3, it'd actually be line 0, line 1, line 2, line 3. For the corresponding connection, you can use index in your expression to get the number of the line. So what we're going to want to do here, what do you think? If we want to assign the dx, how far over this line has to go? What should the expression be? Anyone give it to me? How far over does this line have to go? What's the horizontal displacement that will have to be associated with the line? You can specify it to me in English. So suppose each agent has an x coordinate. Yeah. X coordinate of the other agent minus. Okay, so how are we going to get the X coordinate of, well, let's start with ours, and then we'll subtract that off from it. Ours will be this dot get X, okay? Get X. You'll notice it says returns the current up-to-date coordinate. And you notice it supports GIS systems, which is kind of nifty. Okay, this is how we write ours. So we're going to have to subtract that off from the X coordinate for the other agent, right? And to get the X coordinate from the other agent, well, you might hope there's a get connected agent. Okay, there we go. Get connected agent of index. Why index? Because this says index is the index of replicated line. If this is the 0th line, we're going to get the 0th connection. If this is the first line, we're going to get the first connected agent. And then we're going to ask for his get X. So here, this line has to go over be displaced in X, a span across an X distance of the difference between that connected agent to whom it connects in ourselves, in our own X location. And similarly for Y, just with get Y, right? All agents that are in 2D space. Yeah. And it turns out, and you'll notice this is, see, it says agent continuous, and so there'll be, I should have said agents in continuous space. There'll be some agents which are in a discrete space where it's quantized into rows and columns instead. In which case this same thing doesn't apply directly. Okay, so now, well, you may want to build this just to sort of see if it's a happy camper. It is, and now we can run it, and now we'll see this connected in this sort of way. So that's pretty nifty. We have these agents now linked together. Let's try a few other frogging elements here. So one thing we might want to do is to have those agents over time evolve in some sort of fashion. So perhaps, for example, we want them to have their color change. So maybe when they change state. So if they're susceptible or afflicted, we might want to change. So if we go up to the oval, let's have the oval color change accordingly. So there we go to the dynamic properties of oval, and associated with the fill color of oval, we might say, okay, based on my current state, what color should I be? And again, we could put in a Java expression here. So it might be, state chart dot get active simple state. If that equals susceptible, then we'll make ourselves black. Otherwise, we'll make ourselves red, something like that. Okay. So all I did is I should have said to be clear, this dot state chart, to be pedantic about it. So my state chart, get the name of my simple state. If it's susceptible, then make myself a black color. Otherwise, this is using the ternary operator in Java. Otherwise, I'm red. Make sense to people? Okay. And notice that, of course, the double equals there. We're in C language land, so we have to bow to the compiler god and use double equals. Okay, so if we were to run this now, this is in dynamic properties associated with oval for the fill property, and if we were to run this now, then we have these things that are changing color there. Okay. This is kind of a mixture of some code and declarative elements. It's taking care of calling these things for us. We can simply specify the rules associated with them in a formula sort of way. In a way, it's not all that different from spreadsheet formulas, where it automatically takes care of recomputing this at the appropriate time. But of course, here, these are Java code. We could call up to functions, we could call up to external Java libraries, any number of different things. I want to highlight one other thing, and then we'll break here. And this will get us into the discussion last time. Let's give each of these persons characteristics. Let's give them, say, each an income. So we'll go up here and we'll drag in what's called a parameter. Okay. Now parameters are going to serve two functions. They're going to serve to encode values that don't change much, they don't change at all, but also communicate those values as assumptions. In this case, to the agent. So we're going to drag in a parameter, and we'll call it income. Okay. This income will be a double. So if you look, when we name it income, you could choose the type and you can make it a double, right? And then the question naturally is, well, what do we want to specify for its value? Well, we might specify a default value of $30,000 or something like that per year. And you notice you can specify units here and do some sorts of unit checking. But if you go to main, what you'll go find is that in the population, there'll now be a parameter, or there's a parameters tab where you can actually go and specify a formula that can be used to associate incomes with individuals. So we might, instead of just giving a fixed value across all these people, maybe we want to specify a formula that will be applied to each of them to determine their income. So maybe we have a log normal distribution with a log mean of 6 and a log standard deviation perhaps of 4. And what other parameters does this thing take? It takes a minimum, it can't go below 0 anyway. This is a distribution where if you take the log of it, it's a normal distribution. So it tends to be skewed to the right. It's an exponent of a normal distribution, you can think of it. So it has one of these sort of shorter tails to the left and then a long tail to the right, something like that, which unfortunately is the shape of the income distribution. And here we have a log mean of 5, log standard deviation of 4. So it's the exponent of those that is going to be relevant. And if we run this, what we'll find now, if we go down to the population, is that some people have poor incomes and some people have quite higher incomes. So now we have income distribution associated with this population that we specified through this population. So we have a heterogeneous population now, a population that's heterogeneous in its location, in its current state, and in its other characteristics like its income level. This distribution is specified for this particular population. It could compute these values in any number of ways, and of course, if we looked at this, we could actually have it depend on the index. So we could have, one half of the population be poor, one half be richer, or what have you. But this is a way of characterizing a heterogeneous population using a distribution. So here we've seen some basic elements that we're going to build on next time. We've seen the basic components of the model in terms of the main class, agent classes, experiments. We've seen how we can build up populations of agents that include replicated instances of agents. We could lend those agents a visual representation. We could put them into a network where the network is connected according, in this case, to spatial location. We depicted them in space, spread over space. And we associated some behavior with those agents by the use of a state chart. We saw that some of that same reasoning that we saw in system dynamics with first order delays come directly into play here, directly into play with this rate transition. We saw further we could introduce heterogeneity in the form of parameters, which are then specified as assumptions from the point of creation. So if we have a parameter in person, it is specified in population, because that's what creates the person. If we have a parameter in main, it'll be specified in the experiment, because that's what creates the main class. Okay, general, if you have hierarchies of things, it's the point of creation that will specify the location. State charts will provide a very powerful tool for describing agent evolution over time in a discrete fashion, and we'll be seeing it. Next time, we'll also be seeing how agents can communicate with each other with messages, how that can affect the behavior of the state charts, and we may turn to look at events and how we can use events to sort of trigger occurrences within the model of various sorts. So I think that's all we have time for today. This has gotten us started with AnyLogic. I don't anticipate needing extensively to work with this model, because there's another simple one like it. But if you'd like to save it away and remember, just jot down which machine you are using, you might want to pick up the same machine next time if you've modified. Perhaps some of you, while I've been talking, have been innovating on the model structure or playing around, in which case you might want to save up those models. Okay? So we'll see you again then on Thursday. Keep the questions coming about problem set 2.